Hello friends, welcome to new lessons. In the previous video of moment of inertia, we have seen the parallel axis theorem and some numericals regarding that. Now we'll continue with some more numericals. So I am continuing the video as we have ended with the third example in our previous video. So we start with the fourth example. Here you can see the picture. Here we need to determine the moment of inertia of the shaded region with respect of the x-axis. So just think a bit, how can you do that? We have already solved question number 1 I guess in the previous video. So for this we need to compute the moment of inertia of the bounding rectangle of the whole rectangle. This constitute a rectangle. Then if we subtract this half circle out of this rectangle, then we can get the moment of inertia of the solid region. This is quite simple. So the moment of inertia of the shaded region is obtained by just subtracting the moment of inertia of this half circle with the moment of inertia of the rectangle. So we need to compute the moment of inertia of this rectangle. In the previous video we have seen how to calculate the moment of inertia of a rectangle, and the value came to be 1 by 3 bh cube. Just putting the values 1 by 3 bh cube, we get Ix, that is the moment of inertia with respect to x-axis of this rectangle, is 138.2 into 10 to the power 6. Now we need to calculate for this semicircle part. Now this half circle, in case of full circle, the moment of inertia is 1 by 4 pi r square. So in this case for the half it is 1 by 8 pi r4. So after solving the values, the mathematical things, you can get the moment of inertia of this half circle. Then just by subtracting this part you can get the moment of inertia of the solid region, that is Ix will be Iaa dash minus Ia square. This is just a moment of inertia with respect to this x-axis. This was the moment of inertia with respect to the AA bar axis, and now we have calculated the moment of inertia with respect to x-axis just by using the parallel axis theorem. Now these are some mathematical terms, I don't need to say much here, already these are very simple to know, you can just go through it. So now if you want to calculate the moment of inertia with respect to x, this is the original region or axis from which we want to calculate for this particular half circle. Then it will apply the parallel axis theorem in this case. Then it will be Ix will be Ix bar, that is the moment of inertia with respect to the x bar axis, that is Cx bar axis. The moment of inertia with respect to the original axis as compared to this rectangle what we have considered. So it will be Ix equals to Ix bar plus AB square. So by solving we get 92.3 into 10 to the power 6. Now this is the whole calculation for solving this half circle. Now we have a ready-made equation for this rectangle, so easily we have got. Now for solving this half circle you need to have some mathematical analysis of this geometry or of this particular figure, how you will proceed and what is the easiest way you can get the values. So now we have got the moment of inertia for rectangle and this half circle. So just by subtracting the parts, this part, how will you get this part from this rectangle? If you subtract the whole semicircle you will get this part, and just by subtracting the moment of inertia of the semicircle part from the moment of inertia of this rectangle, you get the value of this solid region. Now coming to the product of inertia, this product of inertia is given as Ixy, that is line integral of x into y into dA, comprising the whole area. When the x-axis and the y-axis are both on an axis of symmetry, the product of inertia is 0 in that case. So you need to remember this point very well. Whenever the x-axis and y-axis or both of them are on the axis of symmetry, then the product of inertia will be 0. Now in the previous video we have seen about the parallel axis theorem. So here is some example, just the equation. Parallel axis theorem of the products of inertia states that in this case Ixy, if you want to calculate with respect to Ixy, the original axis, then just by applying the product of inertia we can get I bar xy plus x bar y bar into a. Clear? So now coming to another example. Actually I have obtained, or I have accepted this example conceptual method of showing these PPTs because the more you will practice with these examples, then the concepts will be clear and you will be able to, in the end you have to solve with these numericals only. So I have chosen how to solve these numericals, and I have main focus is on the numerical part for this chapter. So in this case you have to determine the product of inertia of the right angle triangle with respect to the x and y axis, and also with respect to the centroidal axis parallel to the x and y axis. So just determine the product of inertia using the direct integration with the parallel axis strips. You can take it as vertical or horizontal, then apply the parallel axis theorem. Similarly, in this case we have taken this thin strip parallel to the y axis. So we need to determine the product of inertia with the line integration or the direct integration with parallel axis theorem on vertical differential area strip, that is y is given as h into 1 minus x by b, then dy will be y dx. Simply by putting the values you can get this part. Then you need to integrate this ix goes from origin, that is you consider this as if you consider this as an origin for xy plane, then from 0 to x on the line of x axis it will go from 0 to b, the length. So integrating dix from 0 to b will get, if you solve this integration you will get this value. So ixy will be 1 by 24 b square into h square. Now apply the parallel axis theorem to evaluate the product of inertia with respect to the centroidal axis. Here x equals to 1 by 3b and y bar equals to 1 by 3h, because it lies on the center of the part. So with the results from this previous part, you can apply all those results in this equation. Ixy equals to I bar xy plus x bar y bar and a. So I bar xy will be 1 by 24 b square into h square minus 1 by 3 b into 1 by 3 h into 1 by 2 bh. So by applying this parallel axis theorem, we have got the product of inertia with respect to the centroidal axis, that comes up to be minus 1 by 72 b square into h square. Similarly, we will move on to another example 6. Now for this section, the moment of inertia with respect to the x and y axis you have to calculate. It is given, that is ix is 10.38 and iy is 6.94. The units are in inch. I have collected these questions from various PPTs of teachers, so these are quite clear and this will give you more idea about solving these questions very easily. So you need to determine the orientation of the principal axis of the section about O. Similarly, we will proceed as we have proceeded in the previous all the questions. Compute the product of inertia with respect to the xy axis by dividing the section into 3 rectangles. You can divide this area into 3 rectangles by applying the parallel axis theorem to each of them. Now suppose we have divided this part into 3 rectangles, first, second and third rectangle. It has been named. So you can write the dimensions. Easily you can write these dimensions, how it has been subtracted. Now compute the product of inertia with respect to the xy axis by dividing the sections into 3 rectangles. So ixy will be summation of all the ix dash y dash plus x bar y bar into a. This is the product of inertia. Now note that this product of inertia with respect to the center axis parallel to the xy axis is 0 for each rectangle. That means if you consider this product of inertia with respect to the centroidal axis, which will be parallel to this xy axis, it will be 0 for each of these rectangle, and it's obvious. Now calculating for all of these 3 rectangles separately, for rectangles 1, 2 and 3, the areas are calculated by using the formula length into breadth, that comes up to be 988. Now separately we have calculated the x bar and y bar. Similarly the term x bar, y bar and a, summation of all these terms comes up to be minus 2769858. Then the value for ixy will be summation of x bar, y bar and a. So we have got the value for the product of inertia with respect to xy plane or the xy axis. So these are some simple numericals regarding how to solve the product of inertia. Now we come to the next example. This is the equation of a parabola, that is y equals to kx square. It lies on a xy plane. Now we need to determine by direct integration of the location of the centroid of this parabolic path. So we'll determine the radius of gyration first, then we'll evaluate the total area. When by using either the vertical or horizontal strips, you can find by the direct integration method the first moment, second moments, and then evaluate with the centroid coordinates. So this is the last example, and this example has all the problems or all the formulas which I have solved in the previous 6 examples. Now y equals to kx square. This y, that is, you can replace with the axis b and a. B equals to k a square, so k comes up to be b by a square. Similarly, y can be written as b by a square into x square, and hence x is a by b root b into root y. Now by direct integration, first you need to evaluate the total area. Area is given as single line integration of dA, that is y into dx. The range is from 0 to a, the total length. Just substituting the previous values of y dx, we get ab by 3 as the total area. Now you have to consider any of these vertical strips so that we can find the direct integrations to find the first moments. First of all, you consider for qy, that will be linear integration of xy into dx. All the values are known to us, x, y from the previous slides, into dx. So qy will be a square b by 4. Similarly, qx will be b square by 10. Now that was about selecting the vertical strip and following the direct integration single integration method to find the first moment. Now if you consider a horizontal strip, we will proceed in the same manner, but there will be some changes in this part. This is the total length A, then the equivalent length for x will be a plus x by 2, because this is taken as x. The total area will be a minus x into dy. So by using these horizontal strips, we need to calculate the single integrations to find the first moment. So x equivalent into dA, that will be linear integration of a plus x by 2 into a minus x dy. This is dA. So while taking the limits from 0 to b, that is from limit 0 to b along the y-axis, we get qy equals to a square b by 4. Similarly, for qx axis, that is in linear integration of y into a minus x dy, that is dA. It is critical mathematical terms. So qx comes up to be ab square by 10. Now we need to evaluate for the centroidal coordinates. In this case, xa is equals to qy, x bar a is equals to qy. Now from the previous slide, we have calculated qy equals to a square b by 4, so x bar equals to 3 by 4a. Similarly, for qx, substituting the value of qx in this equation, you get y bar equals to 3 by 10b. So these are some simple examples regarding moment of inertia.